In this video, we'll be talking about work. Work is a product of a force along the direction of motion applied to an object multiplied by the distance it moves. So the first thing we have to understand to do work is the object has to move. If it doesn't move, no matter how hard we're pushing, you're not doing any work. For example, you can push as hard as you want against the wall in your house, and if the wall doesn't move, you're doing no work. Another example would be you can take a heavy mass and just hold it in your hand. You can hold it all day long, but you're still not doing any work because the object hasn't moved. And not only does it have to move, but it has to move in the direction of motion. So, for example, if we take an object, this box, and we push it with a force F, only the part of the force that's pushing in the direction it's moving, and by the way, when we talk about work, we actually replace D's and X's and Y's with the symbol S for distance. Only F of X is actually doing work. Because if you think of F of Y, it's pushing straight down. And what would that do with pushing the object forward in the direction of S? Alright, so let's look at this diagram. If you push this object F at distance S, you did work. So work is just simply force times distance. From this, we can get the unit of work. Okay? Work is measured in joules. So what is a joule? It's unit force times the distance it moved, S. So a joule is just a fancy way of saying a Newton times a meter. Let's look a little bit closer at this equation. Alright, we got a lady that's pulling a suitcase. She's pulling at a distance S. She started here. So she did work. But the work is F cosine of the angle. That's the equation we'll be using. Why is it so? Because this whole F doesn't do work. Only the F in the direction of motion, F cosine of the angle, does work. Now, let's look a little bit closer at this. If we push in the direction of motion, we have cosine of 0. So in other words, if this F was at 0 degrees, in other words, in the direction of motion, the cosine of the angle would be equal to 1, because cosine of 0 is 1. So all the force would do work. In the opposite direction of motion, now imagine this F was not going in the direction of motion, but in the opposite direction, how much work was done? Well, the cosine of 180 degrees is negative 1, so the work done on the object would be negative. And if you pull it perpendicular, now you're pulling straight up, but the object's going to the right or left, that would be 90 degrees, and the cosine of 90 degrees is 0. And you may understand this a little bit better once we do a couple examples in the next few slides. Alright, let's look at this suitcase a little bit closer first. Right, we have a force of 45 newtons, an angle of 50 degrees, and a displacement of 75 meters. How much work was done? Well, not all of that force will do work, because only part of it is acting in the direction of motion. So that's why we have to do 45 cosine of 50 times the distance it moved, and we get 2170 joules. Alright, can work be negative? Sure, if work is done to you. The opposite direction of motion is indicated with a negative sign. Let's take a simple example. You have a tug-of-war. Two teams are having a tug-of-war. Neither one of them are moving. If neither one of them are moving, no work is done. But let's say one team is winning. Well, the winning team would be doing work because they're pulling in the direction they're moving. But the losing team would be having work done to them, so therefore their work would be negative. And here's another example that may be simpler to understand. You have a weightlifter pushing a barbell up. He's pushing the same direction as the displacement. He therefore is doing work. But if he's pushing up and the object is moving down, work is being done to him because it's now the force is 180 degrees from the direction of motion. So work is being done to him. All right, let's look at the idea of an accelerating crate. A truck is accelerating at a rate of 1.5 meters per second squared. The mass of the crate is 120 kilograms, and it doesn't slip. The magnitude of the displacement is 65 meters. And what I would like to know is, what's the total work done by the crate by all the forces acting on it? What I'd like to do is look at each of these forces independently. All right, so here we go. Here's our diagram again. Let's look at the normal force. The normal force is acting straight up, but the object is moving to the right. So the normal force is acting at 90 degrees. So therefore, no work is being done by that normal force. And the weight is also at 90 degrees. So therefore, no work is being done by the weight. So the only thing that's actually doing work is this force static friction. All right, so let's look a little closer at that. Now the angle between the static friction and the direction of motion is 0 degrees. And from Newton's second law, we know that all the forces added up together are equal to mass times acceleration in the x. And since we're talking about the x direction, the only force really is the static friction. And that static friction we can determine if we know the mass and the acceleration of the object. So here we go. The sum of the forces are equal to static friction. We know the mass of the object. We know the acceleration of the object. Therefore, we can figure out the force of friction. Force static friction has to be 180 newtons. Now that we know the force of the static friction, we know how far it moved. We can figure out how much work was done. And there we go. And note once again that the angle between the direction of motion and the force was 0. So cosine is 0. So all this 180 newtons was used in the movement of to keep the object from moving, the static friction. All right. Let's look at the idea of a variable force. But before we look at the idea of a variable force, let's think of the idea of what work is. Work is equal to force times distance. So if we plot force on the y-axis and displacement on the x-axis, then simply the area underneath this curve would have to be the work done. All right, this would be very similar like if we had a velocity versus time graph, the area underneath it would be displacement. So here, if you have force on the y, displacement on the x, you multiply those two together, you get work. So we know that the area underneath a force displacement graph has to be work. So all the problems we've been dealing with so far has had a constant force. So with a constant force, we just know that the work is equal to force times the distance. But if there's a variable force, it's a little bit more difficult. What we'd have to do is break this into little teeny boxes and add up all the little boxes together to find out what that total force would be. And a really helpful tool to do something like this would be the tools of calculus, because with a variable force, you'd be able to integrate this curve and find out the area underneath it. But basically what integrating is really doing is find the area underneath a variable curve or variable function. And for illustration purposes here, what we thought is that, well, if we don't know the tools of calculus, we could break this up into a whole bunch of little boxes, figure out how much each of the boxes are worth, and that's what they did here. The numbers really aren't important, but what they did then is they actually filled in and added up every single one of these little boxes, and when you add up all of them together, you would get the total amount of work done on the object, even for a variable force. Okay? And that's work.